All right, let's go ahead and get started on this sunny afternoon. I know it's a tough choice between attending class and enjoying the weather outside. I think my allergies and I would not be up for class outside though. So here we are. Cool. So what we're going to do to start with is go around, get a feel for where people are at, what they've learned so far. We'll answer any questions you have, and then time permitting, I'll talk more about unsupervised learning in general. I might go over another unsupervised learning algorithm or two. So Dan, what have you learned thus far on this project?
I haven't gotten real far on the project. I've completed all the stuff for math, but I'm still working on the flow drawing.
Okay. Mm-hmm.
Cool. I do have a question about one of the things, but if you, I don't know if you can do that now.
Oh, we can do it now. Mm-hmm.
When we're adjusting, when we're doing the distance by the radius, is that just essentially he wants to take the distance from the upper to the bottom right hand corner of the drawing? Of the song?
So let's.
What do you want us to consider the radius?
Yeah, good question. So let's put one of these together. Okay, that was terrible, but we'll go with it. So what I'm suggesting that you do is, if we've got a side of 4, just go ahead and use that for your radius. So let's look at some examples for how that then works out in practice, right? So let's say that this up here is your best node. So over here, so you've got distances of 1, 2, and 3 going through there. Here you're going to have like square root of 2 or whatever, and then we'll kind of populate out from there. Down here, that is, so this lower right corner, the distance is going to be what? The square root of 18. So that'll be 3 times the square root of 2. Now, and so let's look at how the distance weights work out with these different values, right? So if my radius is 4, and I'm over here, then I've got 3 over 4, so I've got a distance weight of something like 0.75. Over here, I'm at 1 over 4. I have a distance weight of 0.25 to start with, except that then I need to subtract it from 1. Because what I'm trying to do is have the number be a 1 when I'm over here, and then gradually decrease as I go out. So as a practical matter, right, I've got the net distance weight here is going to be 1 minus a quarter, or 0.75. Then over here, for instance, it's going to be 0.5. And then finally over here, it's going to be 0.25. Now, things get a little crazy when we think about this bottom right corner. And the reason it gets a little crazy, right, is that 3 times the square root of 2 is about 4.4 or thereabouts. So if I take 4.4 over 4, of course I get something like 1.1. When I take 1 minus 1.1, of course I get negative 0.1. And so what we're going to do at this point is we notice, oh, this is negative, so that's just going to be a 0. And what that means is that this cell is not affected when that gets trained. Yes?
Is there any reason why we shouldn't just take 2 times the square root of 2 as the radius?
I mean, we could. I mean, the decision is really pretty arbitrary, what we choose for the radius. Using the side is just sort of clear and obvious how we're going to define it. In practice, it hits most of the map pretty nicely. But yeah, it's pretty arbitrary. In principle, you could alter it. Like, this is something you could parameterize the algorithm with and try some different variations. If you're interested in that, by all means do it. It's perfectly fine with me, even though I've given out all this code infrastructure, right? If you want to slap into your constructor for your sum a radius parameter, and then build out your classifiers accordingly and try some variations, that's fine with me. That just happens to work fairly well in practice. The key is you don't want it to be too small. Otherwise, you're not going to get the development of some nice neighborhoods. And as long as we're scaling it out nicely, big values still tend to work pretty well. It's a good question, though. Appreciate it. Cool. Other questions, Dan?
No, that was the main thing I've been curious about right there.
Okay, yeah.
I went with two-scourge and two, but that should work.
What's that, sorry?
The way I have implemented it so far, I actually calculated the diagonal.
Yeah, and that should be fine. And that's a perfectly reasonable way to go forward. Yeah. Cool. All right. So, Austin, how's your project going so far?
I would say not great so far. I had trouble integrating into the code base. I was getting like a weird error that I couldn't even start like running any tests or anything. So
Okay.
I've just had a chance to look at that and fix that.
Okay.
And then, so that's pretty much what I got so far.
All right. Innocent, how's your project so far?
So I have attempted to add the new code base to the last project and kind of run it to see how it goes. But I haven't made any progress towards developing the algorithm.
Is there a point that's confused you thus far?
Yeah, actually, so you said that we need to add this part to our code base from last project.
Right.
But I'm kind of not understanding how it's going to connect. Because when I run the GUI, I don't see anything like SOM popping up in the training part.
Right. So within the code base, what it would need to look like is, I'm going to bring up, I'm not going to bring up my solution. Yeah, sorry about that. I'm kind of a spoil sport that way. But I'll at least explain how the project structure works to help answer your question. So in this project, we've got a handwriting package, and then there's this core package, GUI, and learners. And then within learners, there's Perceptron. For this project within learners, we also want to have a SOM package. Okay, and that's where most of the code I distributed will land, is in that SOM package. Then I also gave this example of the som6.java. That goes in the learners package. What the GUI does is when it starts up, it actually searches this directory for any class that implements the Recognizer AI interface. So anything you put there that matches the interface then appears in the spinner, in the drop-down menu. Yeah.
In my case, it doesn't pop up. I know some 6 extend like SOM recognizer,
Yeah.
but it does not extend recognizer AI.
Yeah. So but some recognizer implements recognizer AI, and so it does.
Okay.
Yeah. I'll look at it after class, and we'll make sure we get it fixed up. But generally speaking, that's how the structure is supposed to work. And if the pieces are in place, it should work fine. Yeah, cool. Eric, what do you got so far?
So because of other stuff, I haven't gotten a lot of time to work on it, but I did get all the test cases working, some kind of preliminary results.
Yeah.
And it looks like it's pretty good as far as like I made a really easy set. Like I tried to be super consistent. Like
Yeah.
every letter exactly the same.
Yeah.
And it's much better at that than the Perceptron one was. But it's actually a lot worse at the other data set that I had, where it can't really handle the variation because it doesn't do like multiple training layers, I guess.
So one thing you can try then is just make the map bigger. If you make the map bigger, it creates more territory, more opportunities for it to find territory for some of those variations. And so that's what I would suggest trying next, just to get a feel for how do you put it in a position to do as well as it can. Now, it might follow from that naturally that if you give it too much map, it could overtrain, kind of like a multi-layer Perceptron can overtrain if you've got too big a hidden layer. But I think, especially given the complexity of that set, it might be worth playing with that a lot just to get a feel for what's a number that's kind of a happy medium. So you might start with an absurd map, like 100 by 100 or something like that, which would have 10,000 cells, and that might just be a way to get a feel for how good can it do at best, and then find variants from there that give you a feel for how it might perform. Caleb, what do you have so far?
I think I'm in a similar situation as a lot of people. Due to time, I've gotten a pretty decent chunk out of self-work map.
Cool.
That's probably about it.
You have any questions yet?
Not yet, but I'm guaranteed I will once I put my
Jake?
I'm almost done with self-work map and hopefully starting on float drawing tomorrow.
Sounds good. Silas?
All I have left to do is finish the train method and the Lego method. I have all the lessons done.
Okay.
I have a question.
Yeah.
Say, to update the node, the average of itself and the example equated by the effective margin rate. Is that just the add the two together, divided by 2, and then also divided by the effective margin rate? Or can you say weighted by the effective margin rate? What is that?
Okay, great question. So if we go over to float drawing, we've got this average in method here. So the idea of the average in method is to calculate a weighted average of 2 float drawings. And so this applies that concept we went over in class last time of the weighted average in the following way. This is actually going to update in place the float drawing that you invoke it on. So you'll actively be changing the pixel values in that drawing. Now, imagine that other rate were 0.5, just for the sake of discussion. What that would mean is that each value from this float drawing and each value from other float drawing would be equally weighted in what this float drawing would finally look like. So you'd have half of this, half of other, put them together. It's as if you added them and divided by 2. What we're going to do is pass as this parameter the effective learning rate. So if you implement it according to the formula here on line 36, where you take 1.0 minus that learning rate times this pixel value plus that rate times the other pixel value, then you'll get this weighted average combination for each pixel. Just by passing the learning rate here and then invoking the method on the map cell itself, you should get your training to be reflected in the map very naturally. That make more sense, Silas?
Yeah.
Good. Will?
I finished coding and started with the experimentations.
Okay, cool. Have you learned anything yet from your experiments?
Well, so far I've learned that 8 layers might be a bit too much to train with self-organizing them.
You have an 8x8?
More like 8-layer sample size. That's what it's about, not by 6x6 X map size.
You've got a 6x6 map size.
But training with the
With 8 letters.
Oh, 8 letters.
8 letters.
Oh, okay. Yeah, a 6x6 map with 8 letters is not likely to go very well.
I'm seeing that
Yeah.
really right now.
Yeah. So how many letters do you think the map is able to represent at 6x6?
I would hazard guess say 6.
I mean, what are you seeing on your map? You should click on the visualize.
Literally nothing. It's still training it right now.
Oh, it's like running.
Yeah.
I was able to do the 8 letters.
On the 6x6?
Yeah, it was very blurry, but it
Okay.
ran.
Yes.
Do you need only one example for each letter?
I mean, it could work in principle with that, but the more examples you have per letter, the more it's going to be able to define a nice blurry thing that covers a lot of the space. Yes.
I assume, do we want to use the same data set for our experiments and routes and this one that we use on the perceptron so we can compare?
Yeah.
Okay, so 10 of each probably.
Yeah. That's what I would suggest. Yeah. It shouldn't take all that long to run, though.
I know. That's what I'm worried about.
Hmm.
Yeah, I didn't run into it taking that long. I mean, I'm running one with 50 now, and it's taking a long time, but
50 by 50?
yeah,
Okay.
it's just fine.
Yeah. So we may take another look at that. So David, how's your progress?
So I think I've got the actual visualization working.
Mhm.
It's working nice, except I'm a little confused with find label for it.
Okay.
Maybe we could go over
Yeah.
not exactly how that's supposed to be implemented, and the KMN part is
did that, but just kind of,
Oh yeah,
yeah.
I'd be happy to go over it again. So finally, sent that off into the stratosphere. So find label for. So the idea of find label for is that, we train our self-organizing map, and let's say it's a 3x3, right? So we've got something like A, H, E, E, A. Oh, whoops, that wasn't fair. Say there's an H there, and then let's just put some E's down here, and then let's pretend this middle guy is just some unfortunate mutant combination like that. Okay. So each of these has a representation of a float drawing. And so the question that's posed is, if this one is the winning cell, what label do we want it to say it classified it as? That's the problem we're trying to solve. So we need to think of a way to say this cell corresponds to such and such a label. So the scheme that I'm proposing that you use is as follows. Once you have, so the first step, of course, is you train the SOM with each example, one time, okay? The second step then is, because the SOM is trained and has these nice values just sitting there, we can then, for each cell, we find the distance between the cell's drawing and every input. Oh, I needed another 4 here. Sorry, just a second. Okay, that aspect is not working. Okay, there. Dang it. Okay, this really isn't doing quite what I wanted. All right. So much for moving it around. For each cell, for each example, okay, we're going to find the distance between the cell and that example. And a couple ways you can proceed from here. What I did in my implementation was I just loaded a whole new array of tuples that had the sample, distance, and its label. You can also use a priority queue to do this. Yeah.
So we're going from the cell to the example, meaning the example is the one that we're trying to
Well, we're doing every training example.
Yeah, but for a specific, sorry.
Yeah.
So you have something that you want to classify, and you're comparing it against every single cell in your grid.
Let's reverse it.
Yes.
We're not actually classifying anything yet. We're trying to build the classifier. And so for each cell, in order to build it, we check that cell's shape against each of the training examples.
I think I had it the other way around.
It's understandable, yeah. So we have each shape against each of the training examples. So my solution was that just gave me tuples of labels and distances. And so at that point, you can just sort the list and then do kind of like k-nearest neighbor. And so this was actually a question that came up in office hours was, well, wait a minute, my histogram, there's no histogram here. How am I supposed to do k-nearest neighbor? And I said, you can borrow your histogram from the k-nearest neighbor assignment. Yeah, just copy that on in, no problem. So sort the list and then find your plurality label from the top K. Yes.
So then if there's less examples, like when you get in your all of the samples,
Yeah.
if that number is less than the K value, you just take
Then just do the, yeah. So in my solution, I actually have min of K and the number of examples. Yeah. Because, yeah, if you go beyond that. And I got a really hilarious bug at one point when I made it the max of the two. Because I had the same number of samples for every label, in its tie break, it just gave every cell the same label, which, while humorous, was not a good classifier. And that's a way you can address that and have it be robust to that situation. Make more sense? Cool. All right. Mitchell, how far are you?
I passed all the tests except for the training test.
Okay.
I think there's just a small bug in there.
Yep. All right. In general, we only had a couple days, so obviously progress wasn't necessarily super big, but still, we've made some good progress, had some great questions. Other questions so far about how this scheme works? Any questions so far about how everything works, how the pieces fit together? Any questions? Yeah, Dan.
I have a general question about the experiment she wants to run.
Yeah.
I assume this is what she wants to do for this is experiment with different size sums and see what size is appropriate to get decent results and things like that.
Exactly. For different groupings of inputs and so forth. What is it that you can visualize effectively? What can you classify effectively and so forth? Yeah. Other questions? Okay, so we've gone over the sum in some pretty good detail, and I think you all have a fairly good sense as to how it works. What I'm going to talk about next are some other approaches to unsupervised learning, and we'll do kind of some comparing and contrasting of what these involve. Overall, unsupervised learning tends to be not quite as popular as supervised learning, because whenever we have an unsupervised learner, we then have to do some additional work to translate what it is it comes up with into terms that actively make sense relative to the application domain. One reason then for the ongoing popularity of the sum is that the visualization it provides of an input space itself can be really valuable. That is, when you first begin to explore a data set, using something like the sum provides a really concise way to get a high-level view of what is in this data set. So even if it doesn't wind up being part of a production classifier, it can still be a really valuable tool just for understanding what's out there, what's in the set. So probably the other super popular unsupervised learning algorithm is called k-means. So your first thought might be, gee, people really like to name algorithms after the letter K. But k-means is a very, very different algorithm than k-nearest neighbor. The idea of k-means is as follows. We obviously have a magic constant k. Okay. So what does k represent? K is the number of categories we're asking for our unsupervised learner to provide. So if we run k-means on something, it's going to classify things into k clusters because that's what it does. So how does k-means go about this? Well, you've got some data set that you're trying to do your learning on. And so the first step, and there are actually many variations of this first step of the k-means algorithm. This is just a very simple and intuitive way to do it. First step is pick k examples at random. So what do these examples mean? The examples are what you might think of as representatives of the entire input space. So how does the algorithm proceed from here? So this next stage is basically along the lines of while no example changes its cluster. So you've got kind of this high level, top level while loop going on. Then for each example, find the k-mean closest to it, and then add it to a list for that mean. So with k-means, then we're going to have k lists representing votes of training examples saying, this is the one to which I feel the closest affinity. So having done that, we then say for each mean, find the mean of its list, replace itself with that mean. And then the algorithm continues. So we go back up, and now we've got this whole new set of means that we generated. And we ask each of the examples, okay, now who's your favorite? Adds to that list, and then we average them all again. And something we're doing is we're tracking for each example, who was its favorite last time, and who was its favorite this time. And if the favorite changes, we have to keep going if it changes for any of them. Eventually, they'll all kind of start converging on finding their favorites, kind of adhering to them, and then the algorithm terminates. Now, is the algorithm like absolutely totally guaranteed to terminate? Well, not really, right? I mean, you can imagine coming up with pathological examples where things just start flipping between a couple of means over and over again. In practice, yeah, it does tend to converge reasonably well. So let's see, let me shrink this a little bit. There we go. So this is the k-means algorithm in a nutshell. This is an extremely important algorithm, heavily used in practice. It's not as much fun as the self-organizing map in the sense that you don't get the nice, pretty picture. But it's nevertheless really useful. Often, when using it in practice, you wind up trying a few different k values with a data set, examining what it comes up with, and then kind of going with the k value that got you something useful or what have you. That's kind of a vague way to do it. There are much more precise ways of handling it as well. For instance, one means of evaluating how well a particular k-means allocation went is to find the mean error for your examples. So part of what we can do is get a sense of how far away on average is an example from its preferred mean. And that can be something that you use as a metric. But in general, there's a lot of seat of your pants associated with this, as is the case with machine learning in general, as I'm sure you're beginning to appreciate. You try to see what you come up with some clusters and go from there. Now, any questions about this so far before I talk a little bit more about its theoretical underpinnings? Yeah.
I'm a little confused about what we're doing when we find these distances in both the inner for loops and that while loop.
Yeah.
So like, for example, I assume each cluster is a list of example data.
Right.
And so I loop through and I find the k-mean closest to it. What does it mean for my example to be close to a list of other examples?
Oh, it's not being compared to the other elements in the list. It's only being compared to a specific mean.
So like an actual, you've got some sort of distance between these things and you've got
Yep,
an average mean.
exactly, right. Yeah, we're unsupervised, which means distance metric.
Okay.
Yeah.
And so I compare it to the average mean in that list and see if it's closest.
Not quite. So let's actually review how the algorithm starts. So it's got this canonical list of k-means. But the question is, how does the algorithm even start? And so a typical way to start the algorithm is to snag k examples at random from the input set, from the training set. So typical way to implement this would be if your training set is an array list, shuffle the array list, and then just grab k off the top. So those are your starting means. Then, looking just at the for loops, ignoring the while loop. For each example, out of those k, we just find, using our distance metric, which one's closest. Okay? Which mean is it closest to? So you've got two different groups of things, right? We've got the means, and then we've got the examples. So if you think of the examples as like E1 through En, and the means is M1 through M, I was about to say N, but that would obviously, MK, right, yes. MK. Then for each E from those examples, we then have to say for each M, find the distance between that E sub I and the M sub J, and then whichever of these is the shortest, that's our winning M. Yes?
Are the M1 through MK actually the k random examples we picked, or are they something that we calculated based off of those random examples?
Both.
Okay.
Yeah, so to get the algorithm moving, we have to pick k at random. And there are some other approaches that are taken as well than just being purely random. One popular variation called k-means plus plus does something where you pick one example at random, and then you have a weighted probability distribution based on the distance between that and every other training example to make it really likely that you randomly pick something really distant from it, and you kind of go from there. It's pretty elegant. It works pretty well. I've personally implemented it and used it many times. But for explanation purposes, this is probably easiest. Yeah.
So just make sure I understand the start of the algorithm.
That's right.
We pick k examples,
Mm-hmm.
and we have to compute the mean for each of those examples, which is our distance metric. What are we calculating the distance between?
We've run ahead a little much.
Okay.
Yeah. So it was a great question, right? So at the beginning of time, we pick our k examples at random. In this first step, we're just seeing for each example, which of the k does it like the most? So we go through, for every example, for every mean, who's its closest match. For each of those means, we then need to maintain a list of everybody who thought that mean was the best mean. Once we've gone through all the examples, we recalculate the means by examining their lists and computing a new mean. So initially, the means aren't means. They're just random examples. But after we've gone through once, we have actual means. So the k are the means of all of the examples that liked that one, that were close to that one. Yes?
In this case, you need to have data that have a notion of calculating a distance in some sense.
Oh, yeah.
So that, do you need to have like a two-dimensional point, a three-dimensional point? Or
However many dimensions you want.
what if it's not even a thing that has a distance of some kind?
If-
A list of names.
Yeah. If you cannot define a distance, you cannot do unsupervised learning. That said, we can be very creative about what a distance is. So give me your example. So what's the thing you can't distance?
Let's say, for example, I have a list of names of people who go to Hendrix.
Okay.
I need to find clusters of names that like each other, and then sort of
Yeah.
create that cluster.
Names that are similar. All right. So, it's kind of a challenge for the class. Given the problem that Innocent just posed, a distance metric on strings, how might we talk about whether strings are similar or different? And by talk about it, I mean assign a number to it. Any ideas? Yeah.
We could start with the length of the name, and then we could take some distance between the letters, compare on a letter by letter, first letter to first letter, and take like the distance divided by 26, since there are 26 letters, we can add something like that.
So that would be a distance metric, yeah. Yeah, Mitchell, what do you got?
I was gonna say, we could like add up all the ASCII values, multiply it by the distance, and then find a difference between two different words.
Right, so we could, transform a string into a number based on the ASCII values. Yeah. Other thoughts?
Calculate the number of changes is necessary to make one into the other.
So what Eric just described is known as the edit distance. And the edit distance is the most common distance metric used to compare strings. So to calculate the edit distance, you try to figure out how many one character alterations do I need to make to transform one string to another. So what do you mean by one character alteration? Well, you could change a character in place. You can insert a character. You can delete a character. Yeah, so that's known as the edit distance. And obviously, it's not super simple to implement, but it's very doable. And that provides a way of talking about whether they're close to each other or not. Somewhat more challenging is how do you find the mean of two strings? Right? So you could imagine doing something like, if you can calculate the edit distance in a constructive way, you could do something like, say, the mean is like if I get halfway, like say I've got an edit distance of 5. Well, all right, let's go with an edit distance of 6 since it's divisible by 2. So I could do a mean of go 1, 2, 3, stop, with one of my possible paths. And that could be a way to do a mean of some edit distances. Yeah.
Okay, so taking this example of names and running through the algorithm.
Yeah.
We'd start out, we'd pick k-names at random,
Mhm.
and those are our initial clusters.
Yep.
And we go through and look at everything in the list, and it would be added to a list with each of our initial 7 names.
Yep.
And then we would go through, and this is the part I'm confused about, find the mean of its list. So say the first one was Kathy, and it's the list of all the names that are associated with Kathy.
Right.
And then we find the mean of the list.
That's right.
What does that mean in terms of our distance metric? Is it the distance between each member of the list and the word Kathy? Or what is the mean of the list?
Yeah, you really need two things. You need a distance metric and a definition of an average, of a mean. Right, a distance metric isn't actually enough. You have to have a way to calculate a mean. And that might be a definition that's independent of the distance definition, but it should be related to it in some way, right? Like it needs to be coherent in some way. If one really gets into this sort of thing, the thing to do is to take the year-long real analysis sequence for the math major. What's that?
More ads. In our probability class, we got nothing but ads about real analysis. Literally an hour ago, she told us to take real analysis 15 times.
Oh gosh, and now I'm hitting it again, right? Right. So this whole notion of a distance metric is the sort of stuff they think about, that real analysis type people like to think about a lot. And those of us in the unsupervised learning world wind up borrowing a lot of ideas from analysts as it happens. I occasionally pepper Dr. Canfield in particular with questions as I'm going over various ideas that I'm contemplating. So, yeah, it's fun stuff. Yes.
So after running this algorithm, you end up with like a list of lists where each list contains words that are
Yes.
friends with each other. And
When you're here, after you're done with that.
Yes.
Yes.
So when you're going to find like an average of each list within that list,
Yep.
do you like maybe calculate this from like each element, every other element, and then divide by the number? Like
In effect, yeah, you want to add all the elements together and then divide it by the number of elements.
you add elements together.
Yeah.
Why What if elements are not one number? Like, is it different from each element to every other element?
So
Adding all elements
Yeah.
together, what does
this
it
is
mean?
kind of where we start having to put our abstract math hats on, right? So we need to have elements that belong to a group in, right? So now we're really starting to